let's say I have a glass bowl down here. That's a piece of glass, and I take say a plastic bag, just your normal shopping bag, and rub it on the piece of glass. Now, after rubbing for a minute or two, maybe, you'll find that the plastic bag would actually attract the glass would actually attract the plastic bag. The plastic bag would be attracted to it if you just let go. But what actually happens is this. So maybe this is my piece of plastic bag. Okay. So what actually happens is that some electrons from the atoms in the glass has gone over to the plastic bag. Okay, that doesn't look quite like a plastic bag. Let me maybe draw something like that. Okay, so maybe that's a plastic bag. So after rubbing the bag on the glass for some time, find some electrons from the atoms in the glass would go over to the plastic bag, so that I have negative charges on here, and that leaves behind atoms that are short of electrons. That means that there would be more protons in the atoms, and that means positive charges in the atom. So this is the kind of thing that will happen when we rub one thing against the other, and then they would actually attract each other. But you can it's quite easy to try this out yourself. Just look for some household material and rub them together. But it is not easy. It is not always easy in places that are more humid. Like for example, if you live in Singapore, where it's quite humid, the electrical charges can easily be removed by water vapor in the air. But if you live in a drier country, like maybe England, for example, when it's not raining, and you'll find that it's quite easy to do this. The electrical charges will stay on the object for a much longer time. I've made here a list of objects, common household objects that you can actually rub against each other and create these positive and negative charges. Now, on the top of the list is where it is most positive, and at the bottom of the list is where it is most negative, in the sense that if you rub something lower down, like a piece of wood, against maybe your hair, for example, the hair will become positive and the wood will become negative. But this is just a rough guide in the ordering. So coming back to this example, so now that we know how to put some positive and negative charges on, say, a piece of glass or a piece of plastic bag, let's try some experiment. Now, let's say I just rub a piece of plastic bag against this and create some positive charges, give some positive charges to this glass bowl. Okay. Now what I'm going to do is this. I'm going to get another glass ball, maybe this time a smaller one, smaller glass ball. I'm going to rub my plastic bag on that ball as well for maybe a minute or so, and that would also give this smaller glass ball some positive charge. Okay, so I have these positive charges here and here. Now, if I have positive charges on two objects, they will repel each other because light charges repel. So this would apply a force on this to push it away. Okay, let me draw this. So I'll draw a little arrow here and draw a little arrow here to show that there's a force from this object that repels, that pushes at this other body with the same charge. And of course, from Newton's third law, forces an action will give an equal and opposite reaction. So this would also repel that with a force in the equal and opposite direction. So that's how we understand, right? Light charges repel. Now, but what I want to look at now is I want to look at the effects of this, the force from this glass ball on charges, on positive charges, okay, in the region around it. Okay, so for now I'm less interested in forces acting on this ball itself. I'm more interested in forces coming from this ball that acts on other positive charges. So let me just focus on this little ball, the force on this little ball. Now I have this little glass ball with some positive charges, and as we can understand now, it will experience a force that try to push it away from this bigger glass ball. Now suppose that I now take this little glass ball and I put it there. Okay, so with the positive charge, then this little glass ball, okay, will again experience a force. This time the force will be in this direction. So you see, the force is always along a direction which is a straight line joining this bigger ball to that smaller ball. So that force as well, that force, the direction of this ball will be along this straight line joining the two balls. So a straight line coming out from here. So that's one of the feature of the force that we can understand. Now the other feature about this force is that if the smaller charge, the smaller object is closer to it, it will experience a force which is stronger. So the closer the charges are together, the bigger this force of repulsion. Okay, so this is another feature of electrical forces. If the two charges are closer together, they experience a bigger force. Right, so let me now think about the pattern of this force in this region of the space around this ball. Now, if I take this little positive charge, okay, and put it anywhere, maybe not very far away, but anywhere close by, here or there, it will always experience a force that try to push it away. So this is a region of space in which there would be an electrical force from this bigger ball can act. Now, such a region of space has a name. It is called a field. A field is a region of space in which a force acts. Right? A region of space where a force x. And we have already seen this description in an earlier video for gravitational field. So this time, instead of gravitational field, we have an electrical field. So this is an electric field. Electric field is a region of space where an electric force acts. So that is the word to describe this region around this positively charged glass ball. Now I want to understand, if I want to understand a bit more about the pattern of this electric field, I want to think about the directions of this electric force at any point in the space. So I can imagine putting a small positive charge like I did with this little glass ball at different points and think about what those directions are. So let me do that. Start clearing all this off. So suppose now that I imagine putting, say, a small positive charge there, for example. Okay, then I know that we'll experience a force in that direction. Okay, along this straight line coming from this glass ball. So we will experience a force in that direction. If I put it a bit further away, it would be in the same direction, but it would be a smaller force because it's further away. And if I put a charge there, it will experience a force also in the same direction, but even smaller. But if I put the positive charge closer to this glass ball, it will experience a bigger force, again in the same direction. Okay, so that's what we can understand. But what if I put it there, for example? If I put it there, it will experience a force as well, maybe about just as big as this, but in another direction, slightly different direction. If I put a positive charge there, it will experience a force in that direction. There, same direction but smaller and smaller as I move further away. So I can imagine doing it at any point. If I put it there, there'll be a force in that direction. If I put it there, there'll be a force in this direction. If I put a charge here, there'll be a force in this direction. Now I can imagine drawing lots of little arrows, everywhere. Maybe just if I start picking at random points, there'll be one arrow there. That point would experience a force there. Charge at this point would experience a force there. A charge at that point would experience a force there. So you can do this to any point at all in this electric field, in this region of space around the glass ball. Now that's a very long-winded way of describing how this pattern of force would look like, of describing what directions they would be pointing in if you put a charge somewhere in the region. Now there is a way to represent this information more directly and visually. This is how we do it. Okay, what we can do is that we can draw straight lines coming out from this positive glass ball. Straight lines going outwards. Just straight lines. But they're supposed to be straight. I'm not drawing it very well. It's not supposed to be wavy like that. Okay. So just straight lines coming out. So this is a rough drawing. Alright, doesn't really matter exactly how many straight lines you draw it. It's just to give us the rough idea that there are electric fields that if you put a small positive charge anywhere in this region, it will experience an electric force in the direction shown by these lines and these arrows. Okay, so for example, if I put a little positive charge there, for example, little positive charge here, it will experience a force in this direction. Okay, and I can tell by looking at these, what we call field lines that I've drawn. I call them field lines. Okay, the field lines is supposed to tell me the directions of the force. So if I put it somewhere in between those two field lines, the direction will be somewhere in between the directions of those two lines. Okay, so in this way, just by drawing these field lines, I can have a picture. All right, at one look, I can see the complete pattern of this electric field. I can have the complete information about the directions everywhere and anywhere in this field. So not only the directions, I can also have an idea of the strength of the force. So like, for example, if I put my positive charge, say there, okay, so I would know that the force is in this direction. Now there's another bit of information I would also know. I would also know that the force here is bigger than the force there. Just by looking at the spacing between the lines, the field lines. Right, in this case, these two field lines are closer together here than they are around here. So this means that when the field lines are closer together, that's supposed to tell us that, that's supposed to represent that the electric force there on a charge would be stronger. Where the field lines are further apart, that's supposed to tell us that if you have the same charge there, the electric force would be smaller. Okay, and the idea of using field lines to represent this electric field, this region of electric force, the idea of using field lines is that we can continue to use it even if we don't know anything about the charges or the object that produces this field. So what do I mean by that? For example, if I clear up this whole lot, including the ball at the center. Now suppose that I am told that in this region of space, there is an electric field, right? And I'm given that the field lines look like this, something like this, okay? And that's all I'm told. I'm not told about any charged object in this region or even near this region. All I'm told is that there are these field lines. Somehow they are created, okay, by something. That there must be some charged object around. But let's say I don't know anything about that. But even though I know nothing about the charges or charged object that created this field, there is still a lot of information in this picture that I can understand. And the information I can understand will be, for example, if I have a charged object here, a positively charged object here, okay, it will experience a force roughly in the direction in between those two nearest electric field. If I have a charged object here, I would have a force again somewhere there, and that force should be bigger than this force because the field lines, the spacing between field lines are smaller. Field lines are closer together here. So I can get this information. And there's also another thing. From these field lines, from these field lines, we can sort of imagine that they must have come from a positively charged object somewhere there. Okay, we can try to imagine it. No harm trying to imagine it. There might be some positively charged object that is not mentioned, and this might have some positive charges. Okay, maybe. But what this understanding tells us is that if instead of having a positive charge there, suppose that I have a negative charge there. Suppose I have a negative charge there. Now I would not have there should also be a force on this negative charge. But the force will not now be in the same direction as the arrows because the charge is negative. Right? It should be in the opposite direction. Right? Which is what we expect if you actually have a positive charge here. So for negative charges, direction of force would be opposite to the directions shown by the field lines. So that's how we can make use of field lines.